We spoke about horizontal asymptotes of graphs of functions, and we said that they were essentially the same idea as having a limit at infinity. But I want to talk a little bit about reinterpreting that limit at infinity to unlock the notion of an oblique asymptote and talk about some stranger end behaviors of functions. But before we do that, let's remind ourselves what a horizontal asymptote is. So a horizontal asymptote occurs when a function has a finite limit at infinity. For example, let's look at the function f of x is 2x plus 7 over x, and let's evaluate the limit as x goes to infinity of f of x. Well, that's the same as the limit as x goes to infinity of 2x plus 7 over x. And again, we don't want to just try to plug in infinity here. We're going to get something like infinity over infinity. And that's no good algebraically. So how about we do our little trick of canceling off an x? So this should be the same as the limit as x going to infinity of 2 plus 7 over x. And now we see that this guy is going to 0, and we should just be left with 2. Okay, so this is telling us that the graph of f of x has a horizontal asymptote at or of y equals 2. And indeed, if you were to graph this function, which I encourage you to do, it would look something like this. And there's a nice horizontal asymptote at this line, y equals 2. Okay, but I want to reinterpret this limit in a slightly different way. I'm going to instead read this as f of x is behaving like the constant 2 near infinity. That sort of makes sense because the non-constant part of the function, if you can call it that, is sort of decaying to 0. It's not really contributing to f near infinity. So f is really behaving like the constant 2. So that's another way of looking at these limits, is a sort of behavior near infinity. And I want to expand on this a little bit because there's other types of behaviors. And that'll help us to unlock the notion of an oblique or slant asymptote. So let's consider the function f of x equals x squared plus x minus 1 over 2x. And we can rewrite this maybe as, let's do some kind of cancellation here. So let's do an x plus 1 all over 2 minus 1 over 2x. And now if we try to naively calculate the limit as x goes to infinity, then sure, this part is going to 0, but this part's going to infinity. So that limit's actually just infinity, which is not very interesting. It still tells us something about our function, but it's not telling us that much. But if we look closer at our function, we see that f of x is x. Let's write it like this. A half x plus a half minus 1 over 2x. And this is a linear function. and this guy is going to 0 when x is going to infinity. Okay, so in line with what we were looking at in the last example, we can say maybe f of x is behaving like the linear function 1/2 x plus a half as x goes to infinity. So maybe that's true. Okay, so we want some more justification for this. So we can play with the algebra all we want, but let's see it and see if we can get the same visual as we're understanding with our algebra. So what I've done is I've graphed the function that we cared about. So this is the function x squared plus x minus 1 all over 2x. And let's see if we can plot that line. So what did we say it was? We said it was a half x plus a half. Okay, so the y-intercept is at a half, and we're going up by halves here. And over here, same situation here. So my line's not the best, but we see that this is a very nice. So this line is y equals a half x plus a half. And it looks like the correct oblique or slant asymptote for f of x. Interesting. Okay, so that does tell us something a bit more interesting about the behavior of our function. Sure, it's still going to infinity, so we weren't wrong, but now we know a little bit more about how it's going to infinity. Okay, so let's formalize this a little bit more. In general, we can say that the graph of a function f of x has an oblique asymptote. So with the equation y equals mx plus b, if the difference of f of x and and mx plus b, and we take the limit as x going to infinity, is 0. So in the limit, their difference is 0. So in other words, f of x is behaving like mx plus b as x is going to infinity. Or I can also interpret that as f of x and mx plus b are canceling each other out as x is going to infinity. Okay, so that's fine and good, but let's verify that this actually agrees with our example. So let's check our example. So we said that our function was x squared plus x minus 1 over 2x, and our conjectured slant asymptote was a half x plus a half. So let's plug that into our definition and see if it works. So we want to evaluate the limit as x is going to infinity of x squared plus x minus 1 all over 2x. And I want to subtract from that 1/2 x plus 1/2. So over here is my f of x, and over here is my slant asymptote. Okay, so let's just do the algebra here. So this should be the same as the limit as x going to infinity of, well, how do I add these together, or in this case, subtract them? I'm going to find a common denominator. So I'm going to multiply by x over x. And if I collect everything together, I'll have in the numerator x plus x squared plus x minus 1 minus x squared plus x all over 2x. And now we see actually that these just cancel, and I'm left with the limit as x goes to infinity of -1 over 2x, but we know that this is going to 0. Oops, going to 0. So indeed, this does check out with our example above. Okay, but we can generalize this a little bit more and say, actually, a linear equation is just some kind of function. What if we considered a different kind of function? So what if we just picked a g of x instead of some line? And then we can say that a function f of x has a g of x asymptote if this limit, so the limit as x goes to infinity of f of x minus g of x is 0. So again, I'm going to interpret this as f of x is behaving like, oops, behaving like g of x as x goes to infinity, or if you prefer, f of x and g of x are canceling each other out. Canceling each other out as x goes to infinity. Okay, so in the previous example for oblique asymptotes, we took g of x to be a linear equation, a linear function. But we could consider stranger g's. And let's do one. So instead of just oblique asymptotes, we could consider, for example, a logarithmic asymptotic behavior. So let's look at the function f of x equals 1.1 to the power of negative x times sine of x plus the natural log of x. I claim this has a nice logarithmic asymptotic behavior. And let's see that. I claim that, well, let's analyze this. So this guy is going to 0 because of the exponential. So we're just left with it behaving like f of x should behave like the natural log of x as x goes to infinity. Okay, so let's test our guess. So let's use our definition from above. So we should have that the limit as x goes to infinity of f of x minus the natural log of x should be 0. So let's do that calculation. And of course, we're just going to get some kind of cancellation here of the natural logs. So this is 1.1 to the power of negative x times sine of x plus the natural log of x minus the natural log of x. And these are going to cancel. And I'm left with the limit as x goes to infinity of 1.1 to the power of negative x times sine of x. And that's going to 0. We could invoke a squeeze theorem if we wanted to here, but that's nicely going to 0. So, yeah, so you say by squeeze theorem if we want to be careful about our reasoning here. Okay, so it seems like the natural log of x is a sort of asymptote for this function. Well, that's fine in theory, but what does that actually mean? So I've gone ahead and graphed these functions to show you what this means. So in the red, I have f of x being our function 1.1 to the power negative x times sine of x plus the natural log of x. And in the blue, I have our g of x being the natural log of x. And indeed, it looks indeed like g of x is a, or we can call it a logarithmic asymptote for f of x. So really all these end behaviors of functions are kind of saying some limit about as x goes to infinity. And we can have all sorts of different kinds. There's almost as much end behaviors as functions. There's many functions that have the same kind of end behavior, but there's a whole new world of different kinds of end behaviors that exist there. And oblique asymptotes and even horizontal asymptotes are just a special case of that. So if you're anything like me, in high school, oblique asymptotes were a little spooky. I didn't really know where they came from, but actually they were just special cases of these kinds of end behaviors, and there's so many different kinds of end behaviors to explore.